So I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. So today is a lecture number 9. In this lecture we will going to see the heat transfer or convective heat transfer coefficient and how it is important in the case of convective heat transfer, and what are the some parameters. If we change some parameters, then what will be the effect on that convective heat transfer coefficient. So let's start this today's lecture. I am Amraraj Sawant, Assistant Professor from Department of Mechanical Engineering. Before starting this lecture, we have seen that three modes of heat transfer, that is conduction, convection and radiation. So in conduction, the most prominent factor, that is convective heat transfer coefficient. So how this convective heat transfer will going to change some criteria or some parameters regarding the convective heat transfer, that is what we are going to see in this lecture. So convective heat transfer coefficient H, the convective heat transfer coefficient is usually denoted as H, as we have seen in earlier. So it is a property that quantifies, this is the main word. So it is a property that quantifies the rate of heat transfer between solid surface and the fluid, means liquid or gases, flowing over or near to it due to the convection. So it is a parameter that quantifies how much heat is going to be transferred from solid with respect to the flowing fluid around it, and at how near to it in the convective heat transfer. So let's again take an example of this heated slab or heated metal piece. So whatever the temperature of this heated metal piece and whatever the flow of air over this, the heat transfer coefficient quantifies how much heat energy is transferred from this metal block to surrounding. So here the figure illustrated same thing. So here we can consider a hot plate, okay, and over this hot plate the air, or you can say any fluid, is flowing with some velocity. So the convective heat transfer coefficient H over it will mainly quantifies how much, means it's mainly prominent factor that quantifies how much energy or how much heat will be transferred from this hot plate to the surrounding. Okay, so this is heat transfer due to the convection Q, and the flow of fluid over the hot plate, which is shown by these arrows. So T1 is the temperature of hot plate and T2 is a surrounding temperature. So here the convective heat transfer is a main prominent factor that quantifies how much heat transfer or how maximum heat transfer will going to be from this hot plate to the surrounding. As we know that the heat transfer only possible when there is a temperature difference, and here the temperature difference is also there, but the flow of fluid and that properties of that flow like density, viscosity and velocity is mainly dependent and is mainly calculated or mainly sum up with the convective heat transfer coefficient, which is denoted as H. So basic heat transfer equation, that is Newton's law of cooling for convection heat transfer, whether the convection will be natural or forced convection, the same equation is used for calculating how much heat will going to transfer from hot plate or from any solid to the surrounding. So Q is equal to H into A into Ts minus T infinity, where Q is a heat transfer rate, and H is a convective heat transfer coefficient. Its units are watt per meter square Kelvin. So here A, in some books it is denoted as AS, where the A or AS is surface area of that plate where the fluid motions are in a contact with that surface area. So Ts is a surface temperature of that hot plate or any solid, and T infinity is a bulk fluid temperature or the ambient temperature or a surrounding temperature where the fluid flow is there. The surrounding temperature or the fluid flow temperature or a bulk means average temperature of that fluid flow. Okay, so basically this H means the heat transfer coefficient or convective heat transfer coefficient is mainly dependent on the fluid properties. And what are the fluid properties? Viscosity, density, thermal conductivity. And how these H will going to change with the change in viscosity, density. Let me give you some example. Same hot plate is there. So if the viscosity of fluid will be less, okay, then less viscous fluid, if we pass through it or pass over it, then H will be more and heat transfer will be more. Okay, if the density of that fluid flow will be less, then the H will be more and heat transfer will be more. So similarly, the thermal conductivity, if it will in thermal conductivity case, it is reverse thing. If the thermal conductivity of fluid flow with that fluid molecules, if it is more, then the heat transfer will be more and value of H will be more. So nature of fluid flow. So if the nature of fluid flow is a laminar, then H value, H means convective heat transfer coefficient, will be less, and for turbulent the H value, that is convective heat transfer coefficient value, will be more. And you just think from this formula, that Newton's law of cooling formula, that whenever the H value will be more, then the heat transfer takes place will be also more, because they are in a directly proportional way. Okay, so heat transfer is a directly proportional to the convective heat transfer coefficient. So by this, if the laminar flow having H value, if it is less value, then the Q, that is heat transfer, will also be less. Okay, in turbulent, H value, if it will be the more, then Q value, that is a heat transfer value, will also be more in turbulent case. Okay, so it is a general thing, because heat transfer is directly proportional to the convective heat transfer coefficient. Okay, so geometry and orientation of the surface, that also plays an important role for quantifying the value of convective heat transfer coefficient. So temperature difference between the surface and the fluid, as I have given an example in before lecture, that if the temperature of this metal and the surrounding fluid temperature, if the temperature difference, if it will be more, then the heat transfer will be more. If the temperature difference of this hot plate and the surrounding air will be more, then the heat transfer will be more, or that there will be the chances for more heat transfer. Okay, so physical meaning of H. The high value of H, whatever I just said before, the high value of H means the fluid quickly removes or delivers heat. So how quickly the heat will be removed from the system will be dependent on the value of H. H means convective heat transfer coefficient. So if high value of H, the fluid flow of high value of H, of high value of convective coefficient is there, then there will be the chances to remove the heat or to extract the heat more quickly. Okay, for low value H, the fluid poorly removes the or delivers heat, or vice versa. If lower value of H of that fluid flow is there, then there will be the chances to remove the heat very slowly. Okay, or poor in poor way. So this is the best example of forced convection, where high value, this is a best example of forced convection, and this is the best example where low value of H is natural convection. Okay, So microscopic view, and why does this H varies? Likewise, in the second slide, I have said that this H, convective heat transfer coefficient, is mainly dependent on the fluid properties like viscosity, density, and thermal conductivity. Also, the fluid orientation or surface orientation, or also the fluid flow, or that is a velocity. It is a laminar flow or a turbulent flow. But in on microscopic view, how does this H varies? So first, the heat is first conducted through the thin layer of the fluid near the surface, and that is called as a thermal boundary layer. So then it carried away by the motion of surrounding bulk flow. So there is a two main basic differences or basic steps behind this variation of H. Again, let's consider this plate as a hot plate. Okay, let's say this is the first layer of molecules of fluid which are getting touch in this hot plate. Okay, when this thin layer of fluid are getting touched in this hot plate, then the surface or a thin layer where the first conduction of heat takes place. Okay, first conduction or first absorption of heat takes place, that is called as a thermal boundary layer. Okay, and after this, second layer of fluid will be there, and that second layer of fluid will cause a motion, okay, a motion like this or in any direction, and that motion will be causing a heat transfer afterwards. So these are the two main aspects. First is a conduction where the heat hot plate will be getting in a contact with the first layer of a fluid. So there the conduction happens, and again with the further layers, the motion of the fluid layers will cause the heat transfer, that will cause in a convective heat transfer way. So these are the main microscopic view to vary the H value. So H will depend how thin boundary layer is. Okay, if this boundary layer which are getting in a touch with a hot plate, if that is a boundary layer where very thin, then H value is more, as it is written here. Okay, and how fast or turbulent motion of fluid or a mixing, then value of H will be higher. So what is mean to say here, after this first layer, if this first layer having thickness very less, then the H value, convective heat transfer coefficient value, will be more. And after this first layer, whatever layers are there which are in a motion, okay, the first layer also is in motion but in a slow way, but after this first layer, the whatever the layers are there, and when they are in a motion, then how fast that motion will be there is mainly cause of higher value of H or higher value of convective coefficient of heat transfer. So the nature of fluid, that is water, conducts heat better than the air. So nature of fluid, what type of fluid you are using. If you use for this heated plate, if you use air, okay, and in second case for this heated plate if you use water, and third case is there for this hot plate if you use some certain kind of coolant, then whatever the heat transfer is going to take place is different in both cases. And why it is? Because these three fluids, let's say air, water and any coolant, having specific capacity to absorb heat. Okay, and so that is a different according to their different structures or structure of their internal molecular level. So that will be also going to affect the H value, which is convective coefficient of convection. So typical ranges of H. So we have seen this for free convection or natural convection, the H value will be more or less, okay, and for free convection in liquids is more than this gaseous. Why it is so? Because the liquid is having capacity or more capacity to absorb the heat. So the liquids in free conduction having the H value, that is the convective heat transfer coefficient value, is more than the gases or air. So forced convection in gases will be in this range, but this value will be more than free convection or natural convection value, and forced convection in liquids will be having higher value than this. Similarly, boiling, this is another kind of a phenomena. This is very complex phenomena, and you can't model this boiling phenomena easily. So for these some complex empirical formulas are there, because in boiling the heat transfer takes place in, let's say, for example, with a 3 or 4 types, and how these with the pressure and temperature the boiling happens, and to model this is a really difficult task. So in this course you are not going to deal with boiling, but just to understand how the value of H will vary, the boiling has highest value of H, which is convective heat transfer coefficient. In condensation of steam also the H value will be higher side. So factors affecting the value of H, just before we have seen, I have put it in a tabular form. So properties: viscosity, density, thermal conductivity, specific heat to consume a heat, specific heat of any substance to consume heat to rise its temperature from 1 degree Celsius. So these properties are very much affecting the value of H. So fluid velocity also, just I have stated that the higher velocity fluid, the higher value of H will be obtained. That is the thinner boundary layer. Whenever the boundary layer, which is the first layer which is going into contact with this hot plate to transfer the heat in a conduction way, so this layer, when it is will be the thinner, then the H value, convective heat transfer coefficient value, will be more. So surface geometry, orientation, shape, roughness, and these impacts boundary layer development, and whenever the boundary layer will be the less, then the convective heat transfer coefficient value will be the more. So temperature difference, for not for only H value, whenever in a heat transfer there is a more temperature difference, then the heat transfer will be more, or the chances to extract the heat or the chances to transfer the heat will be more. So heating versus cooling, the coefficient can differ depending upon the direction of heat flow. So in heating and cooling, this convective heat transfer coefficient will differ depending upon the direction of flow, where the heat is going to flow from hot end to cold end, but the direction of flow means the fluid flow direction. So whether the fluid flow direction or heat flow direction will be reversed by some external work. So this is depend on the direction of heat flow. So how H influences, means convective heat transfer coefficient influences the heat transfer behavior overall. So let's see this. In still air, that is a natural convection, we have known that H value will be lower, so the poor cooling we can get and the heat transfer will be slow. Okay, and fan blow air, that is forced convection, the H value will be more than this free convection or natural convection, and moderate or good cooling we can obtain. For boiling water, the H value, as we have seen in earlier tabular form, so H value will be more and extremely effective cooling we can get. For condensation of steam, that also the H value we have seen in last table. So H value is highest at this condensation of steam, and rapid heat transfer we can achieve. So that's why in condensation of steam, the cooling towers, in first lecture I have given that example of evaporative cooling. So the evaporative cooling, the rapid heat transfer we can achieve for our power plants. So misconception about this H. So convective heat transfer, which is denoted by H, is not a fixed property of material. It is dependent on the property of the fluid flow. So how the fluid flow is going to vary? Let's say for example, if the fluid flow having a velocity, let's say 1 meter per second, and afterwards its velocity increases, then the H will also increases. So it is mainly dependent on the properties of the fluid flow. So same here written as, so H is not a fixed material property like a conductivity in a conduction. It is dependent on the situation like fluid speed, temperature, viscosity and density, and etc etc. So the heat transfer performance can't be judged only by the temperature difference here in a convection. In a convection, we can't judge the heat transfer, overall heat transfer, just because of or just we have taken consideration only temperature difference. You must have to take a consideration these factors, that is fluid movement and the geometry of the surface, because these are going to change the boundary layer thickness, and whenever the boundary layer thickness will be lesser than the higher value of convective heat transfer coefficient we can get, and when the higher convective coefficient value we can get, then the heat transfer will be more. So for higher value of H like boiling, the phase change effect are involved and which are complex to model. Likewise, I just said before, the boiling is literally a tremendous, or you can say a complex phenomena, and for modeling the boiling is literally a difficult thing, and you are going to see this in detail in your core subject in your third year of engineering. So these are some misconception about H, because in conduction we have taken that the thermal conductivity is a property of material that is not going to change with respect to situations, that is going to change with respect to the different types of material. But in convection, the H, that is convective heat transfer coefficient, will going to change according to the type of flow or the properties of flow. So these are some misconceptions about convective heat transfer coefficient. Thank you very much. So I conclude this lecture here. So the assignment will be given of 20 MCQs for this lecture, and you will find this online link in the discussion group. So feel free to ask me anything about this lecture in a discussion forum. So you will have the lecture PDF also in that discussion forum. So thank you very much.